start your presentation.
Okay, can you guys see my screen?
Yeah, very clear. Yeah.
Okay, so my topic today is particle convention in laminar non-newtonian fluid, and it is a pept and cfd approach. And the whole part is divided into 4 sections. And the first section is the aim of this research. Let's say the particle liquid flow is encountered in many areas. For example, for the macro scale, the mixing of fruit into yogurt in food industrial. And for the micro scale, like blood flow. And the main challenge for the solid liquid multi-phase flow is because of its complexity. And also most of the technology that we are using to understand my multi-phase flow are they require for the transparent system. For example, for the blood flow, they are opaque, and some technique like LDV, they cannot get the information from the blood flow because it's opaque. And in the University of Birmingham and in the physics department, there is a machine or there is a technique called the positron emission particle tracking. And this technology can give us information from opaque system, which means that you cannot say what happened inside, but because the R rate light can get over the fluid, so you can get information from a detector. And then on this part, I can explain to you guys later. But anyway, the pept, the positron emission particle tracking technology can deal with opaque fluid, which is its advantage. And also we are using cfd models and software to predict what will happen in our fluid. And the second part is our experimental setup. This is a flow rig that we are using to test the pipe flow. We can start from this is a closed loop, and we can start from this pump on the right side. This pump will pump a certain amount of liquid, which this pump can control the flow rate. And this pump a certain amount of the liquid into the first tank 1. And the tank 1 will mix it to make the whole multi-phase system to be homogeneous. And then because of the gravity or the height of this pump and tank level to the pipe, and we can make this height to be constant. And the gravity with the height of the liquid, which is caused by the gravity, will give us a force, or let's say a constant velocity in the pipe system. And then the particle and the liquid in this the tank 1 will deliver to the pipe. And you can see this red square. This is a part that we are detected by a detector. And the fluid information can be catch up in this area. And then after here, then it was sent back to the tank 2. And then the tank 2 will send it to the tank pump. And then the whole loop is recycled. And this is what it looks like in our system. The first part is the solid particle is the glass bead, because it is much heavier than the carrier flow, so it is settling, and then you can see at the bottom of it, it is like fluidized bed, which means kind of like fluidized bed, and then the bottom of it is stable or moves slowly. And the second part, the solid phase is alternate beads, and the density of the alternate bead and the carrier flow is very close, which makes the whole system to be homogeneous and well suspended. And now I'm going to introduce the positron emission particle tracking technology to you guys. Let's say when we have a flow, and then we will put a tracer, which here is this red particle, into the whole system. And this positron emission tracer, it will emit the radioactive lights, or let's say R rays, and then the R rays can be catched by the R ray detectors. And as you can see here, those for example, if this particle, it emits two R rays, and then it will go to two different positions, and then will detect by the two detectors. And if we connect those 2 points in the detector, then it is a first line. And then if this tracer has another 2 opposite R rays, then it will have another 2 locations detected in the detectors. And then if we connect those 2, then it will be another 9. And those 2 lines get together can let us know where the particle was at that certain time. And those lines is called a line of rays, which is LOR. And then by those lines, we can detect, or we can figure out where the particle location is, and then we can know at what time the particle is. And then it will give us a data file like this. By the position and the time, we can get the velocity. Because, for example, at the first second, it was at a position, and for the second second, it was at another position, and then we can calculate the velocity by the different position with time. And this is how the detector looks like. If you see the first picture at the left hand, those 2 detectors are just on that circle, and our pipe will go through that circle, and then when every time a tracer passes through those 2 detectors, the position of those tracers can be detected and recorded, and then we can know the velocity of it. And then the third part is my simulation. And the simulation is because now I'm dealing with the laminar case, and the force that added in on the particles are a kind of, let's say, relatively simple. What I just consider is a drag force and the lifting force. The first is like I use ANSYS SafeX to build up the whole system, the mesh, and then set up those models. And then I try those, and then I produce the result to check with the pept data. This is what we this is the result that we are detected. The points and the black points or the squares that you say is the velocity distribution of the pipe, of the cross section of the pipe. let's say, for example, like this. Here, here, this is a pipe, and then for different position, we can have a different cross section. And then, for example, this velocity profile that we have is at this condition, which is with this flow rate, and the solid density is 1020, and then the solid volume fraction is 0.3%, let's say 30%, and then the diameter of it is 10 millimeter. And what we found is that the velocity that we get actually is the average velocity that cross this detector. I mean, the detector, it has a length, and then the velocity that we can get is the average velocity of that whole cross section. And the interesting things here is that you can say the velocity, as the pipe length increase, the velocity is developing. And because initially for the single phase laminar flow, after the entrance length, it will get stable. But for the particle liquid phase, the velocity is varying with time. Just like these pictures, you can see the shape of the velocity distribution of those 6 pictures. They are almost the same, but the maximum velocity is different. And if we look into this picture, you can see, let's say those velocity profiles come from those pictures, because their maximum velocity and the other velocity are slightly different. And you can see from time 5 seconds after 20 seconds, the velocity distribution is changed, which means that the velocity of the laminar flow in the pipe will vary because of the settling effect. You guys can, if there is any question, you can ask me later, or you can record and then ask me later in the question section. But anyway, here what I want to say is that the laminar case will, because the laminar case, the fluid is separated into layers, and then when the particles is going down, it will keep going down and cannot go back, not like turbulence case. And then because of this reason, the velocity distribution is always changing and cannot reach steady state like what we are expecting in the single phase flow or the turbulence flow. And this is my conclusion. And another point that I missed is here. Normally for the homogeneous system, the velocity profile is symmetric along the center line, but our velocity profile is a little bit up, let's say off the center line. And this is also because this neutronian buoyant system is not homogeneous. And then the second conclusion is that the particles will settle and then can't reach a steady state along a certain distance. And the third conclusion is that the CFX can give us a good approach or good agreement with the PEP data that we are using. I finished my presentation, and if you guys have any question, free to ask me.
Thank you for presentation, Zhuangjian. Yeah, thank you. Yes, I have a question. I wonder, can you explain a little bit about in your experimental setup, what is the principle to checking the position emission particles? Yeah. This figure.
You mean here?
Yeah. I cannot follow that. You just explanation. Can you explain
Yes.
a little bit to me? Thank you.
Let's say in this picture, the red circle, it represents a tracer particle, and this tracer particle is radioactive. And every time it let's say as time goes by, it will emit gamma rays. Do that make sense? And those gamma rays can be detected by the detectors. The nice thing is that the gamma rays can go through those substance. For example, if it's inside the liquid, and it can go, those gamma rays can go through the liquid and then get into and then touch the detectors, and then their location can be detected by the detectors.
Okay, and yeah. Thank you. Yeah. You explained very good. Is that the gamma ray will activate the positron?
The gamma ray, let's say the tracer is radioactive by the cyclotron in the physics. I mean, they had a cyclotron that provide radioactive water, and then we will use those water to grab, and we will put the tracer into those radioactive water, and then the tracer will grab some activity from the active water, and then this tracer is radioactive. Does that make sense?
Yeah. Thank you for explanation. Dear attendees, do you have any question? You can raise your hand or